Squeeze theorem. So before we attempt this problem, let's do a little review of what the squeeze theorem really means, because I think a lot of people think it's harder than it really is. So let's just do a quick little picture. So the basic idea is that if you have two functions, let's suppose you have function f, and I'm just going to draw this kind of arbitrarily. I have no idea what function f really looks like, but maybe it looks like this. And then you have another function, function g, and again I'm just kind of randomly picking, and this is not so random, that part there. Alright, so that's function g of x. And the idea here is that the g function is always less than the f function, right? For any value of x on this entire interval from, say, a to b, from a to b, the f function is always greater than the g function. And maybe they just intersect at this point of tangency where they're the same, so they're not greater than at that point, they're actually equal to. But everywhere else, the f is greater than the g. And then now I'm going to introduce another function, I'll call it the h function, which is always between f and g. It's always between f and g. It's just floating along, it's always between. And it just squeezes in there, which is why it's called the squeeze theorem. And I'll call that function h of x. So the idea here is that g of x, the smallest one, is always less than or equal to h of x, which is always less than or equal to f of x. In other words, h is always between g and f, or equal to. So at this point, we suspect that h is equal to f and g because f and g are the same. And if h is going to be between them, h must be the same as well. And that's the idea between the squeeze theorem. If you know, and you can show, that f is always greater than g, and that h is always between them, maybe you can't find the limit of h, but you can find the limits of f and g. So the limit of h is implied by the fact that it must be between f and g. So if that's still a little confusing, we're going to apply it to this problem and you'll see it in practice. So we have this expression, we have this x times square root of 2 plus cos 1 over x plus 1. What makes this a little bit tricky is the fact that we have cosine 1 over x, so we couldn't make a direct substitution here if we wanted to, because if we put in 0, we'd have 0 times this whole thing, which seems like it would just be 0, but then inside we have 1 over 0. Now what's the cosine of 1 over 0? 1 over 0 is an infinitely large number. But the cosine oscillates forever, right? So as theta becomes or x becomes larger and larger, the cosine function just keeps going up and down and up and down and up and down. So we don't know for an infinitely large number what the cosine will be. So what we do know is that the cosine of x, or the cosine of 1 over x, cosine of anything, can never be outside of the limits of negative 1 and 1. At its very smallest, the cosine can be negative 1, and at its very largest, it can be 1. So let's imagine that it was as small as it could possibly be. Then this part would become negative 1, and then we can rewrite this expression. So we can say that x times the square root of 2 plus negative 1, all under the square root there, plus 1, is less than or equal to this whole thing, x times square root of the original 2 plus cos 1 over x plus 1. Why can we say that? Because we chose for cosine of 1 over x the smallest value that it can ever take on. So if we put in the smallest value cosine 1 over x could ever take on, negative 1, then what we get out as a result must be less than or equal to the original, right? Because that's making the cosine smaller is going to make 2 plus that number smaller, which is going to make the square root smaller. It's going to drag down the magnitude of the whole expression. And by the same token, we can use the same principle and say that let's now let cosine 1 over x be as large as it could possibly ever be. The largest it could ever be is 1. And what happens in that case? Well, then we get x times square root of 2 plus 1 all plus 1. And now let's simplify these. So this guy is going to become 2 minus 1, which is just 1, and then the square root of 1 is 1. So this whole thing just boils down to x plus 1. And that's going to be less than or equal to this again, which is x square root 2 plus cos 1 over x plus 1, which is less than or equal to this, which is 2 plus 1 is 3, square root of 3 times x. So I'll write square root of 3, I'm ready to give myself a little room, square root of 3 times x plus 1. So we know all three of these functions are continuous, just like our f, g, and h. And we know that this thing in the middle, this whole expression here, is like our h function. It's always between g, right? It's this function that's always smaller than or equal to it. And it's between that and its upper limit function, f. This is as big as it could ever be. So it's getting squeezed between the two. So in order to find the limit as x approaches 0 of this thing, it must be between the limit as x approaches 0 of this function that's always less than it, and the limit as x approaches 0 of this function that's always greater than it. And let me put these in parentheses to show that. Now we can't, like I said at the beginning, we couldn't conveniently by direct substitution find out what this limit is, but we can find out the limit of this thing that's always less than it, right? We can make a direct substitution for x here, and it just becomes 0 plus 1, which is 1. So the limit of that function is 1. No big deal. And on the right, we can make a direct substitution of x here as well. This term goes to 0, and the limit equals 1. So the limit of this whole big thing is always between 1 and 1. So what happened? It got squeezed in between the two. Its limit must be 1 as well. So the limit as x approaches 0 of this whole thing has to be in between those two numbers, which are the same number. So there's nowhere else for it to go. It has to be 1 at that point. And that's the final answer.